So we'll just give an introduction. So we, as Yogi said, maybe general driver architecture and model will go through close to 1 hour. Another 30 minutes we'll go over Wi-Fi. Okay. So one of the agendas for here is, as you guys, both of you are mostly working on application side, we'll just try to just focus on what are the different kind of devices, generic devices available, and how to implement and framework for a device driver. Basically, what all the things would be involved in it. And this would more focus on platform drivers for any kind of platform specific driver, which is given overview of the device model, how a Linux device model would be there available, and how you have to hook onto the device model for your driver to be up and running. So we'll focus on one of things like serial ports, frame buffers. This frame buffer is nothing but the X window system which use guys work. It's more to do with the graphics and USB network driver, and we'll just focus on a generic platform driver. Okay. So yeah, I think you guys are aware that there is an user space and there is a kernel space for Linux, and previously most of the drivers were written on kernel, and anyway the kernel space was getting clogged up because you cannot go beyond your system RAM on kernel space, which was predominantly for 4 GB RAM and 1 GB, the one which is allocated to kernel, and 3 GB was user space. So people used to keep using the kernel space, and that's where the focus was moved on to write user space drivers. So most of the time currently the industries have already moved on to write most of the things on user space as much as possible, and keeping only the services to be run on kernels. Okay, so there are 3 specific types of devices generally you would come across when you say device drivers. The first thing would be the character drivers. This is the most common, as it has been mentioned, because you take an TTY serial driver, or even I2C or SPA or GPIO. So there are so many frame buffers, serial ports. So even graphics, everything, sound devices, everything is using on serial devices. So it's all character drivers do character and byte by byte. So that's the predominant devices you would see at most of the people would be working upon. And the next set would be the block devices, which is mostly the storage devices. If you have worked on storage network or something, you would have seen all SCSI SATA drives, and also the external cards like flash cards, wherein now everything has been moved up even to flash. Even you have your OS on flash and start booting up from it, because it's very faster and it has many write cycles, and the boot up time is very fast. So there are pretty much that is much going on the block devices as well. So it's a very huge demand on the block devices drivers part. And next one is the network devices. Oh, here also the industry is working too much on network devices, and predominantly it boils down to 2 set of drivers. One is the wired one and wired, another one is wireless. Both mostly boils down to the Ethernet driver, but at the MAC or the PHY layer, it depends like how you are going to use it on a wired basis or on wireless basis. That's how it changes over to an wired or Wi-Fi driver. And there is some point-to-point connections as well. You do it through a network. There is a flip, and there are many kind of devices that comes across which does only an point-to-point network communications, because it doesn't have an capability like Wi-Fi to go beyond, but within a short debug and console connectivity, they use this point-to-point network devices as well. And yeah, so we were trying to focus on network. So let's talk about network devices. I think you guys would have already used some of these commands because you were saying that you were working on applications. Maybe any user who has used only on shell programming or shell in Excel, he would have used these commands, but these were written with kernel drivers. They would have populated it through sysfs and other virtual file systems within your driver. But you would have used these commands without knowing it's underlying. It's an egg. Internally, everything is an C library written on kernel and populated to it. Predominant is the if config, where you can configure all your interfaces, whether it's Ethernet or anything. And there is something called as route, which basically involves when you do any kind of networking, when you do any ping outside your computer or anything network, that's the command uses. You can even say where I want to route it, how I want to route it, if you have a network card. So anyway, you need to have a network card to communicate with the outside world. So we would talk about it. We would talk about the socket interface. Basically, when you talk about network, it has to go through socket interface. How you can use a socket interface, the socket buffers, and how you can send it through the network. That we'll talk about for in the upcoming sessions when we start up beyond the demos. So that's about the how to at the outside layer, how to access network devices, because anybody who wants to understand how it works, they can run through the set of commands with the options to see what all been integrated with it. If you know the details, then we can, if you go and write a driver, you'll know okay how they're related actually. And for the block devices and the character devices, predominantly you need to have any kind of set of operations for any devices for at all. So when you write a driver, you need to say this driver is going to have some set of operations. So for any device, like you have a network, you have NDO, so and so network _ OPS or operations, whatever. So there you define your APIs, which would be used by your users. So when you do a ping, or when you do a TCP dump, or when you do any kind of FTP, so all this happens from the outside application level, but internally it boils down to system calls. So these are the system calls which you would have defined for your driver, saying how we are going to access them. So most of them will have this open, read, write, and close operations. And open is the one which is the actual driver interface. So when the device gets, sometimes people write a driver wherein it happens the every device initialization at the BIOS level. And most of the time currently the industry has moved over to, like, when you do just do a device open, only when you try to access your device, that's the moment you have an open call being invoked for it, wherein you do the initialization. So because I think you guys would have been aware that in kernel you write kernel modules, because there is something that comes attached with the driver or the kernel itself. You write drivers which is for the kernel, and this comes with the package within the kernel. But there is something called as module based kernel. So you have a kernel module, you write and invoke it, which won't be part of the actually next distribution. You can just keep adding to it. So the module based drivers is the one most of the people will rely on. And for that to happen, people generally go through this open call, wherein only when the device is being used, I will just populate it. Otherwise, it will sit without using any kind of space, just to make sure it doesn't clog up any kind of more memories and stuff. And when you say unread and write, as such, it is, as you know what it is, like you do your reader library calls read and write, send or receive packets or whatever, and close is nothing but whatever you did the initialization, you would be doing the reverse of it. And it needs to happen the reverse chronological order. Means you would have enabled the device, you would have allocated memory for it and stuff, and you have to do the reverse part of it. Means you have to remove the regions, and the last thing you would be to disable the device. That's how you have to do it. Whatever done in the open, the reverse has to happen in the close. And network doesn't use this major and minor for a driver, but the block devices and character devices typically use them. So major and minor is like you have an vendor, and the vendor would be called as like an major, and minor would be you have USB device. That's a major part of it, and minor would be the USB is for a camera or USB is for an audio. So any device needs to have this major and minor number so that it gets add on to the kernel. Otherwise the kernel doesn't understand this driver boils to which device I couldn't get. So when you want to add these to the kernel framework, you need to have an unique numbers for this, and you have to obtain it from the vendors or the one who is providing to you, or even if you have a PCA or if you want to write it, there is something there group for it, PCA dev IDs. So you need to go and grab the information from them and use it, saying that I have a driver. Then you go through the framework and obtain a number and get it upload from them to be part of the forthcoming Linux platform or distribution, whatever. And there is something called as special files, because you write drivers and sometimes it could be part of your virtual file system or special files. So that is, you would have seen /dev ram /dev this whatever. So these are like special files you would write a driver, and it just comes up and goes. It doesn't take too much of memory, because these are almost like daemons which runs, and you can use them as well. And you need to have this. This has been created with make note command, and typically this has been done with this user device. So this is like general way the framework how and drivers will work. Right, so
what is daemon?
Daemon is like an user process or anything which runs in the background. So you won't be even aware that there are so many daemons that is running in the background. Like Linux will have bin init. It's a process. After the init process done stuff, they will go in background. When most of the you have projects, anything you want to implement it's like a monitor software. You write a monitor software and put it in the background. It will keep checking whether anything is going bad, and anything is going bad, it will take a call and bring it. So generally we use kill process everything to kill the daemons. Otherwise, because you write a program in daemon, you should be very careful, because you write a program in driver and you make it as a daemon running in the background. You have to be very careful, because with the memory, otherwise it will keep shooting up your memory, and you won't know whether your buffer has been used up and you go out of your memory. That's why you have to be very careful with daemons, because people would implement so many devices and stuff and even programs, and they execute as part of the background daemon process, and they won't know how it has been used or how it is getting exploited your systems. So we have to be very careful, otherwise it will come and hit you in a way which you are not even aware. So we'll cover the daemons as well, like how in Unix or Linux systems the daemons are there, how you can even view it, and how you can even implement it and stuff like that.
So this daemon is like services we are having in Android. In Android
yes,
we
yes,
have services.
Yes, all the services will be daemons.
Okay.
Yes, they get invoked only when you use it.
Okay.
Yeah. We'll just run over some of the slides. This will go into detail, because character drivers, you would have these kind of so when you say any drivers, you will have this framework. You need to have a structure for it. When you say network drivers, you would have seen something called as the net device structure. When you say character drivers, you would have seen CDEV structure. So basically this is like a big structure. It's been like a framework or pattern that has been given, which will have all the attributes considering or required for implementing a character or a block or a network driver. and this is where you can keep adding your information, or you can populate your information. So there is nothing much you can keep adding to the structure. Most of it's already been defined, which covers all the part of it. Only thing is you need to be aware how the structure is going to be used by me, how I am going to make use of it so that I'll populate in a way it's required for me, and what set of operations I'm going to use on those device structures. So for character drivers will be like file operations. So since we told it's a TTY device or something, you would have a file operation. You will have a LSeek or FSeek to write or read from a device or something at moment and send it across. For anyway, for block drivers, you would again have something called as GenDisk, general disk structure, and you would implement block device operations. So like what all stuff needs to have for this driver. And similarly for network drivers, we would elaborate on net device structure. So there is huge information. You can we would be even sending you the path. You can go to the Linux drivers. You can say /linux netdevice.h, which would have elaborated the structure in a way. So when we say structure, there will be a structure union within the structure. So this is like a parent structure which has everything put together. So the net device might even have for an Ethernet device. It might even for point-to-point connections. So everything is put together a generic device. You just use it what you want, only that part of it. So you can go and manipulate only the data structure of the parent structure which you are concerned and start implementing. But rest of things would be like a null or something. You would have given zeros and initialized it. And for network drivers, you have net device operations, wherein you typically like same open, write, close. And there are some other things as well, like you have power management. You need to have your shutdown, resume operations, wherein you need to work on low level, means low power modules. So we'll talk about that later, like how to implement those device operations and what all would be necessary, what all would be an add-on when you write your device drivers. So as the first line says, the device drivers must register themselves the core kernel. So this is nothing but when you have any kind of driver, character driver or network driver, anything, you say register chardev or register netdev. So we have to register this device or the driver to the core kernel. Only then it will get populated during your system firmware and the BIOS, or when the device gets open, because the kernel needs to be aware that there is a device that is hooked on to me. So only you register that framework to the kernel is aware there is who else sitting on your kernel and what all its operations and what it can do. So when you populate these device structures, after that you have to go and register that device onto the kernel. So only then, so when you register itself, you need to have these operations. This is my device, this is what I'm going to do, and what you're going to do would be populated as part of your operations, whether it's file operations or net device operations or block device operations. So this is a typical thing you need to be aware, like what goes inside the kernel. Right, so if you're an application, you would have seen mostly at the top level, like this. You might know some C libraries or system calls. You would have used open or write. That is just like a top level system call, but actual system call like would be sysread or sysopen or syswrite. That's the actual system call the kernel internally invokes. So whatever you are saying is an application program interface API, but the actual system call internally will happen. So why you need system call? Because you are mostly working on your user space at these layers, and you are talking about a device driver where you are going to exploit the hardware to do some job for you, because either there isn't a driver which is new you are implementing it, or there is a driver you are increasing or implementing a new feature to it. So you need to talk about with that hardware, and only one guy can talk with the hardware, that is the kernel. So the kernel comes this side. So when you want to talk with the kernel, you don't have the privilege. These are called as privileged operations. So only the kernel has the privilege to do anything on the hardware. So to get to that kernel level, you need to make a system call. Only then you move from user space to the kernel space, and then you now can handle any hardware or any the address space which handles the drivers. So you can basically do a read or write or anything on the devices once you reach to that level. So that's why you make any kind of system calls, open or read or write, or even if you do if config whatever route, everything is a system call internally goes and jumps onto the kernel and then do anything for you. So the C library is nothing but the glib or GNU, or it kind of can have any kind of libraries. I'm just saying predominantly it will have libc or glibc. That's a library generally. You do all malloc, calloc, whatever you do it like a C library. And we say system calls. There are some system calls like mmap and stuff which does something with the memory management. There are so many calls. I'm just giving you an example at what that system call actually meant, because you would be allocating somewhere like I want this memory, but internally it might use a system call like mmap or brk or srk, sbrk kind of system calls to actually go and talk with the kernel and allocate a page table for you and give a physical memory map allocated to your virtual memory, which is attached to your process space for any process you are running into it. So that happens at the system call level. And yeah, so when you talk about with the any kind of character drivers or block drivers, anything, they'll talk about, can you just give an overview of what's a network stack? So or any kind of character or block like a device driver or device layer stack. So that stack is nothing but specific set of APIs and everything which does your call. When you do even a ping, there is something called as you do a send and receive. But within your network stack, you would talk about implementing them, like you would have a socket interface, or you would have a file descriptor in character devices to make that happen. So these would be the internals, like a kernel internal for that. So which would be part of your stack. So that's the actual thing which does the job for you in your lower level. So these are the typical architecture. You have the applications, you have a C library to implement something which is like at the AP level, and then the C libraries will make the actual system calls. So when you do open in C library, that's an API for you. And internally, it does a sys_open, which is a system call. It gets onto the kernel and then does your job for you, like doing a file descriptor open or doing a console open, whatever internally. And then that gets interfaced with your drivers, whether it's your character driver or block driver or network driver. And typically you would have like network, you have network stack, and in block layer you have this page, cache, and IO scheduler. So depending on layer it differs, because you need a cache in block because you are going to do an bulk transfer. So you need a cache which we can speed up your operations. Otherwise, the CPU would be clogged up with too much of instructions you are doing only for your IO bandwidth. So you need a cache, you need a DMA controller or DMA channel to really bypass this and directly talk with your driver. You just put in here. So your drivers itself might have some system RAM or buffers onto it. So directly you can talk with your application and your driver, and you can bypass your CPU doing all these kind of virtual memory, physical memory transfer, and block doing buffers. So you can talk directly with your driver buffers and your application. Directly you can put it into your system memory from your device memory. That can happen by bypassing through DMAs and other different features available. So that we can talk about when you do with implementing your drivers. So this is a typical architecture, and person needs to be aware like what all stuff that involves in a kernel or a device driver framework. So this is, we are not going into detail, just to put in applications like how it has been done in device level, that's why we're talking about. So in a character driver, if you want to implement it, you will have a file operation. So what all those set of operations? So generally you might need to have an LC to position your buffer or the pointer from where to you want to write or read. That might be an LC, or you have to read the whole set of file, or you want to do an full read and write. So these are the typical set of operations that happens when you do on character devices or even in block devices. Both happens almost similar. So these are some of the operations. It might have more than that, but most of these typical things falls for any kind of driver when you want to write it. It would have an IOCTL. Typically you need to have it. So in detail we can talk about how an IOCTL allows you to interface with your drivers. So whatever you see in outside world, it's been because everything will be called as a kernel object, how the kernel object is populated, how you can see it, the statistics of any device and everything, that all gets populated by implementing IOCTL. So IOCTL is typically an interface for any kind of doing IO operations with your device. So you can use an inbuilt mechanism comes along with it. So you have a open, you have a flush, because you have a cache in block devices. You want to flush when something is written. Otherwise the cache coherency is not in place because you have updated something else and it's not been flushed out. So you are having a stale memory, which is like you have updated it, but you are going to read an value which was previously written, not the updated one. So you need to always flush to rewrite or come up with a refresh. It's basically you do a page refresh. That's how the flush also works. And you have sync, everything is part of it. Like you sync it, you do a refresh and come back and say your DMAs and all cache, everything is coherent, all reading the same latest memory or memory region or value. So this is for typically for character or block devices. You would use these kind of separation operations to register onto your kernel. And okay, so you can see it here. You would have an write operation and read operations. So this is the place you would have these are like function pointers. You would have for an Acme device. I'll have an Acme read and Acme write. So you are setting up a set of operations for your device. So this is the function pointer. It would invoke when the device gets opened and initialized, or even when you are doing an actual read or write. So these function pointers have to be implemented with your functions. So this is just we have given like an overview. Like this is a typical way you would have implemented your read or write call and then give the function pointers. And these gets registered when you do a register character dev or whatever the device. So your operations are registered. So the kernel knows what sort of operations you are going to use it. And typically it jumps over to that function pointer and just invokes that. And your operations on the device is being handled. That's how typically it happens in a kernel. And these are the character driver skeletons. So when you say skeletons, like we were just only talking about registering a device and stuff. So when you have any kind of device, so the make device is there. You set up an major number, minor number. It can be static, and you have something called as to do dynamically, wherein it will go dynamically figure out what is an unused number and allocates to it. So that also you can do it. So you can allocate through a static way like makedev, or you can do it. The kernel itself will figure out what is the unused number and provide it to you, which you can use it for an driver. And as we told about struct cdev, demo cdev. So this is the device structure we were talking about. So you need to have a device and you need to have what is my device numbers, major and minor, so it's get registered when you do an register device. This is a device that gets onto your kernel framework, and you need to have the structure populated to say what all I'm going to use in the device structure. And you need to go and register your device. So until you don't register with your core kernel, the kernel framework is not aware like what all the devices hooked onto it. And there is something called a cdev init or cdev add. So there are so many functions, but some of them is like cdev init, which does beyond an device initialization what all it needs to have. So you have done your register character device regions, like what all the regions it is going to use, memory regions. Basically you might map your device memory onto your system memory. So what you write onto your device, it's like you are directly using your system RAM. So why you do it? Because the access will be faster, because you can't directly access your device memory that needs to have all this MMUs and everything. You have to go through different layers to go and touch up the memory of device. So when you talk about any frame buffers or you do a X window system, so X window everything uses an character driver, and they have mapped the X window system buffer, video buffer onto your system RAM. That's why whatever you do on your console, everything it pops up so fast and you wouldn't even know it, because this is touching up with the system memory, which is actually mapped to your video buffer memory. So you won't even see it, because these all you have done as part of your registering your device itself. And this cdev init is nothing but what set of operations I'm going to do with the device. And you add something to it, because one of things would be here like a demo count or something. When you do one device itself, you might have a reference counter attached to it, like who all using my device, whether everybody has revoked or everybody has given up after they have finished it. So the kernel might needs to aware like this might be needed to just if somebody is exploiting too much, and if they finished it or they given up the resource back to the kernel, so the kernel is not worried about too much resource being taken up. So some people even are advised to have a reference count of how many devices being used, who is using it. That all would be also part of your operations. And these is a reverse of it. So you have a init, you do all these kind of operations, you do an exit, you need to delete the device, you need to disable the device, and you need to or unregister your regions, whatever allocated to you. Basically you have done a mapping of your device memory to system memory. You need to put it back, because that system memory can be used for any other process. So you have to basically unregister them and unmap any kind of demo buffers. This is like you create any circular buffers or ring buffers, whatever in network, you just create only for that moment. It's like temporary buffers. You use it, and once you have done with it, you have to reverse it. So these kind of buffers would be used in character drivers and network drivers. You have something like socket buffers. So these typical ring buffers or any kind of things would be you need to give it back to the system once you done it. So this is like a typical driver what all needs to have at least a minimum requirement, but depending on your device things might have many operations, but typically you need to have an init and exit where you initialize and you do a deinitialize and you call up those modules, and so that whenever your device has been called up or it's been opened or a device has been shut down or whatever, the corresponding operations are being carried out. So which is part of your device driver framework. So some of it we will run over. So device usage. So you can so okay, you have done your device driver and everything. You have you consider even attached it. So how I can go and use the device now? How I can really run the device and see whether things are working fine. So we are just given information how to do it, like create an device dev demo. So these all use the udev framework. This is a character device, what all its major and minor numbers. So device is created, Then you do one file descriptor, open the device, do a read or write to it. So this is how you do it typically at the user level. Once your device has been initialized and hooked out to the core kernel framework, then you can go and test the device whether it's really working up from your Linux shell or system programming calls. You in your like you can say that's a driver program. You can write a driver program to see whether your device is actually working as expected. So these things probably will skip it now. You won't even understand how it has been used internally. So as we talked about how a typical framework happens, what all things happens in a device, what is definite requirement to have a device driver involved, and how you can test it. This is internally like what all things you can still add up. Like you can create your own read-write system calls to a driver and stuff like that. That we can go in detail once you go through the classes, because this will be too much at the current moment. Yeah, so we have just given this information to just understand like, okay, what typically an read or write operation generally would do it. Anyway, you would have an file descriptor and do kind of operations like this is an asynchronous read or a file operation read. So how you do a read, how you do a sync, so like notify access and synchronize. So what generally goes through when you write an typical operations to a driver, just we have given an overview, like what all you need: a file pointer, you need a buffer, you need a count of how much you are doing to write. You might even need to do one position, like you position your buffer to do a read or write onto your character or a file, whatever the device is all about. Okay, this is a major part you would be requiring in any device. We are not going to into the details of it, but this IOCTL is mainly used to, this is the main line, like it allows you to extend the capability of a driver with driver specific operations. Basically, you can keep adding your device capability. So you can add it and you can say it beyond read and write. I can allow it to do like changing the speed of a serial port, setting the volume of sound card, configuring video related parameters for framebuffer X window systems. So these things typically won't be handled in the already given driver framework. So your driver framework might have a set of operations like file operations or block device operations, network device operations. But when you write a driver, because you are writing a driver for your own, and it might need to have beyond the features which is currently available within your framework, and that's where these IOCTL comes handy for you. It provides a mechanism for you, like a framework where you can exploit your device and increase your capabilities. So it is like how it does. You can provide device parameters to it as a parameter or arguments to it. So and within that you can implement it like, so this parameters or arguments, what I'm going to do with it. So you can go and add the features or capabilities with your device, so that that now gets part of your framework. It's all been registered after the device is being used. So that will be typically done by your IOCTL. So at the kernel space or stuff, that's how this will be used. Like it's a file pointer, it's a function pointer, which you can do like in so many device drivers you would say do IOCTL. So as part of your driver itself you would say I'm going to do IOCTL, but do IOCTL would differ for different device, and there it would talk about what kind of device operations I'm going to do for that set of device. So typically for a block device you might say I have an inode structure, what I'm going to do with it. I have a file pointer, what I'm going to do with it. So the different capabilities would be incorporated with IOCTL. It's a very major part of your device driver mechanism. So yeah, just given an overview of how it has been done. That's it. So we have file operations. So you are saying an IOCTL, demo IOCTL. Normally you will have do IOCTL, and you will talk about passing these arguments to it, like what this function is going to do with it, and you start. This is like we have just given so demo command. So you just like user command itself, or even command line option. You can give it, and depending on different set of commands, I'm going to perform different set of operations. So what would be there? It depends on your usage. So this something would boils down to the actual functionality we're going to implement for that IOCTL functions. Well, that's a typical mechanism. So herein you would see like how you are going to use, because anyway this is also a system call. So how you are going to use it to open the device, and with that device I'm going to do some kind of operations. I got the file descriptor. This is the command, demo command 1. So these are all these commands would be registered part of that IOCTL functionality. So which anyway we have done with an switch case. So this command typically what it has to configure it, you would be configuring as part of your IOCTL. Once you have configured it, now you can go and use the operations, because that device has been initialized with that functionality. So like increasing your volume card as we told, or increasing the video RAM, the buffer. So that's been exploited. Now you can make use of the functionality after it has been registered. So this generally would be using like a configuring mechanism to configure your device to do something beyond what is already there in the framework. Okay. Kernel framework most drivers not directly. Yeah. So some things when you see the device driver, sometimes you won't even know whether it's a character driver or block driver. You would have like a generic driver. So which won't typically even jump to being part of a character driver, block driver. So this all be typical in different framework itself. So some examples like you have a frame buffer. Anyway, it's a character driver, but it has beyond something as a character driver. So there is a separate framework for it, framework buffer. Similarly, even a TTY, which is a serial, and V4L, or typically you would have heard about at least frame buffers and serials. So these are typical framework, which is like it internally uses a file or a character or a block, but it has something beyond to it. So there is separate frameworks for frame buffer driver or serial driver, serial port driver, everything. So which has something more device specific framework implemented it. So there are so many frameworks, not necessarily only it will boil down to your block device or character device or network device. So there are different frameworks which is customized or factorized, which takes from the common. It's like inherited. It inherited the properties of character or block, but it has more than that. You won't see it typically in your network devices. That's why we haven't given it. But if you see a character device or block device, there are so many devices that's been pulled out and given a separate framework. So like frame buffer. So we would talk about in detail like how a frame buffer works. So any kind of graphic cards, everything comes through it, or T2A serial port mechanism, everything comes through a different framework, which is something beyond our extra extended capability of an character or block device. Okay, so we're talking about frameworks. What framework? Yeah.
What is this frameworks means? Like the similar type of drivers we collected together, or what it is means?
Yeah, that's where we're coming into it now. So,
okay.
So we have just given an example of a framework. Yeah. So when we say framework, it's as you would know it, and as Yogesh mentioned, it's like you have some framework is nothing but it's like library function if you're not even aware. So you create a set of libraries or something available to you, and just you go and make use of those library functions, because you don't want to write and malloc now, or you don't want to do any kind of something. So it's already available. You can just use it. But if you want something beyond an malloc, I want to know how I know how a memory management works. So I'm going to write my own, because malloc has some problem. It takes only from brk or sbrk. I want to write my own. Then you go beyond the framework. But it's like, don't reinvent your wheel. So if there is something available, I'll just make use of it. So any new sound card driver comes up, so they typically use this kind of frameworks, ALSA core framework or something. But as I told, there is an IOCTL coming in picture that can go and extend your capability, because many people would do it's a copycat. They just do the same thing and give a new name for it. But somebody would go and extend the driver as well. So you go and use a framework which is available in your kernel and do something beyond it as well. So these are the typical things of the framework. So when we say framework, people have all the system calls attached to it to get onto a character driver, or to get onto an graphics card, or to get onto your block device or a network device. So the framework boils down to your system calls associated with your drivers. So you make a system call open, then you do one sys open, then character drive gets involved to do one read or write along with it. Similarly with your sound card, similarly with your graphics card. So this all is part of the kernel framework already available, or so many people have already given the framework and done it for different set of device. Just many people, if you want to do and jump onto a driver, just do a copy of it and then extend something beyond for your references. So that's like a framework. It's like already an glib C or something as a library, and mechanism is already available to you. So that's why we told you need to register to your core kernel, because a framework is available. You make use of the framework, like net device structure or file operation structure. You take the framework, add something onto it and register to it. So you have registered a new framework onto an existing one. So the kernel is aware, okay, now I have an addition to it. I know what this addition means to me. So it knows when to call and how to call and what all operations goes with it. So if you understand the framework and how it has been internally used, then it's easy to go and do any extra manipulations to it. Like in serial device, you have serial core and your driver. So when you talk about why the framework, because core functionalities will be part of your serial core. There would be something like common, something will be default. So that would be part of your core, and the serial driver would be the actual driver structure. You go and do something extra. So this core would be like common functionalities. This core will talk with your general core framework, so which is already provided. But if you want to do something extra and extend the capability, that would be part of your driver. The core would be attached to your driver, and your driver will get an extended capability. So you have something already framework, use it and do beyond. Same way, even if you have a block device, in network device also you'll have a PCA core, you will have a PCA driver. So everything might have a core of common functionality with the framework, and you go something beyond it. So similarly, even in block layer also you have SCSI core, and you have lib88 just to do a SATA kind of device, and you would have something to do with a USB kind of storage, because everything is a block storage. You can have an USB storage, USB drive, or you can have a SCSI device, or you can have a SATA device for storage, or you can have an SD card and everything. So there might be a core functionality to do with any kind of block device. But see, I'm not the guy. He has something different. I am different. So he would provide an extended version of within an library, or you would say, I have something different. Then you go and write your own driver, but you take the existing mechanism or existing framework. So you need to understand the framework first. This would give an idea to whether you want to go with the already existing framework or you need to create your own. That's how even a frame buffer, everything started evolving beyond that character driver. So if you understand the framework, you would get to know that your device fit into it, or you need to create your own, or you can just make use of something in it and keep adding something beyond that in your specific driver code. So for that, understanding of framework is very important. Okay.
Consider like if we are having someone new display, we have to interface. So like
Yeah.
which kind of like whether we have to use the framework or like how
Yeah,
it will fit.
that's why. Yes, correct. First, you need to understand your device, what all needs to be done with the device, and the device functionality has to be aware. Then you always need to know about what is existing. So most of things is already happened by the frame buffer itself. So if you have an understanding about the frame buffer and you say, okay, I don't think so it is going to have any use for me, then you can create your own something that gets fit onto it. You create your own tree here and say, I have a new buffer framework, or I have a new serial device or CATA device framework, and you can start doing it. And there is no reason for you not to stop doing it. And you have done it, and you added something, a new device tree onto your framework. And if everybody accepts and saying that, okay, this is not going to exploit anything on my kernel system, because everything is being taken care with the driver handles it, and if something happens like panic or something or trap, this guy is handling by its own, so he's not going to exploit the others onto the network. As long as it does that, you can keep adding. That's how frame buffer came in picture. That's why this came in picture. These all are part of character drivers, even this TTY. So all are internally character drivers, but they have something specific to it. This is with the sound card, this is with the graphics card, this is with something point-to-point character driver, like you are for only for UART and stuff. So you have something specific to it, then you can create your own device tree and do a device framework for it. So if you have a good understanding of the existing framework and you have a new device in coming picture, you are very much sure in the early stage itself, this is not going to work for me. I'm going to create my own. But anyway, you would be extending this. So this has to happen. You need to, there is a system call, because anyway you would have an open or read or write or anything. But this open is going to do something different than what these guys were doing it. Then you can create your own extended capability and you can attach to the kernel system. So that's how there is a two provisions, right? Either you can create a new tree structure which will be part of the existing kernel, or you can extend the framework with a kernel load module. So if there's a loadable kernel module, so you don't even figure out. So only when there is used, this guy comes and attached to the system and gets removed. So this is not even part of your existing framework itself. So as long as that you don't even have a problem with the actual the kernel guys or anybody to go and say, okay, I don't think so your driver needs to sit in there, because if you create your own loadable module, that gives a go more easier thing for the kernel framework, because they don't bother, because it's only used when it being used. So you're not coming up with every framework. Why that is necessary? Because if any new kernel comes or any next version comes, they don't want to worry about attaching your device and say whether your new versions is going to have any effect on your code, or whether this code is not going to run on the new version. So as long as that's why people tend to do any kind of loadable kernel modules, that won't be part of your actual kernel. But if you configure it, that's why we had the next slides, how you can configure it, say that this is going to get attached to the already existing framework, means for every kernel this will be presented it, or will be only presented as like a daemon, or as a sitting as a sleeping device, and I'll just use it whenever it comes, like a loadable. So that you can do as a config mechanism with your make files or whatever the build system. You can say this driver is going to be present in the kernel, or it's not going to be present. It's going to be only loadable as and when required. So any device driver you can hook up with this and say this is again a frame driver, but I have a name for it, like ALSA. I have a new name for it. Or you can create your own framework and you can create your own driver, which gets attached to the kernel or gets attached as a module, kernel loadable module. So it depends on your necessity and your understanding. So as long as you are sure and you can go, and because anyway everything gets reviewed because it's going to get added onto a kernel. So once you have your confidently saying that this is not going to be of any use for a device and they're convinced, they allow you to create a new structure within your kernel framework. That's how it is. Okay, so I think I answered that, right? So yeah, so anyway we'll jump over. So if you need the slides we can give it. So here we talk about what's the kernel options. So that's why I was talking about, you have to say config frame buffer. So even in your driver code you would see something like config_config, if def, only if it is configured then I'll have some operations to it. So we'll have a generic character driver. So within that you can have this conditional compilation and say if defined config this so and so means this guy have some information, and I'll go some operations attached to it. Like typically when we cover network drivers, we'll talk about a network driver can work like an interrupt mechanism, or it can even work polling mechanism. Most of the current network drivers works in a polling mechanism, wherein you collect all, scatter or gather your information of all the buffers and send it as one package. So you don't keep transmitting the data for every data coming into your device. You would, okay, I know that there are so many devices coming in, I'll keep adding to it, and you'd be polling, okay, everything is done, then I will do at one shot. So wherein you will go and see whether config poll has been done. Only then you create some controllers or in memory or something to do kind of this polling mechanism to attach to it. So it all depends on your kernel options, what all things you have configured it. So that will be part of your build system. You can go to your Linux kernel, you will see make menu config, whatever you do it, that is nothing but you are configuring your kernel for it. So the make menu config, you would see like structure, okay, it has an debug option, it has some character drivers options, network driver options. So everything is internally boiling to one config underscore something. So only whatever you configure it will be part of your kernel. So there you would say yes or yum or no. So yes is going to be part of your Linux tree, your Linux kernel tree. And you say yum, no, it's a loadable module. And you say no, saying that okay, it's not even loadable, it's not going to this, it's just going to be sitting in there, not going to occupy any space. Well, as and when I require it, I'll just populate as part of the tree or loadable module. So that's how you build your system as part of your kernel, how your device is going to be used in your system. So that will cover about it, how an kernel option has been used and how you register the numbers. So you can even go through all the header files that will talk about the attributes being part of creating an character driver or major minor devices or frame buffers. What are the frame buffer options there? That structure you can get on to see it, because only then you get on to see the structures, you will know that whether I need to write a device from scratch or I can use an existing one and just add something. You can even go on some add on something to structure, or you can even create my own FB operations. So depending on the need you can do it, but you have to be very careful. This has to go through the open device driver framework, so it needs to get reviewed. So you need to have a proper reasoning being said in the reviews to make sure that whatever you have done is the proper way of handling it, and you have a reason, it gets added on to the kernel framework. We'll jump over these things. Yeah.
Actually, when we do that make menu config, no, that time we do M, but those packages also gets built, right?
It's get built, but it won't get built onto your kernel. So that would be, when we say built, it is built, it means compiled. So anytime you want to use it, yes, it's only compiled. So it's not been allocated something like a kernel within your kernel system. So it is part of your distribution, but you can use it whenever you wanted it. It is like you have library sitting in there, but this is like a DLL, dynamic link library. So you do the dynamic linking only when it's required. So as long as that is, it is still sitting in there. Like you use a p thread or something, or kernel threads, that library is still there, but nobody is using it. Only when you go and do one link p threads or link whatever, only then it gets linked. But it's compiled and built for you. That's it. So it's ready, but it's not part of your kernel. Means you say a core services kernel layer. That guy is not aware. Okay, I'm not aware of this guy, but I think it might be there, because how you will know it? Because when you do a device open, that time that guy gets linked. Okay, then the kernel gets expanded. Okay, I know now who is this guy. So for that, and compilation is required. That's how you do AM. So when you do AM, it gets compiled and built in, but it don't go and get add on to your kernel.
Okay.
Yeah. This talks about more upon the frame buffer, and I think we talked about this some time back. Like typical, this is a skeleton, how the operations would be part of your drivers, and this is like init is nothing but almost this is like the driver program, like so init. So it's like main program, but you are going to use your driver inside the register my framework. These are the operations, allocate the device, and what all the operations I'm going to use it. So there is an FP info. This is nothing the device structure, and for this device structure, what all the operations I'm going to do it. Then you register that framework with the core kernel. So these are the typical things needs to be there, like as it's told as a skeleton, needs to be there as part of your driver. So to expand it, so just given it for information. And here we're just talking about more on devices. We'll jump on it. What we are trying to talk is, when you have a device driver, there are two, three mechanisms. You would say there is an adapter to it, there is a bus driver to it, there is an actual device driver to it. So this all will be part of yours. You need to understand what is a bus, what is your device doing with the bus, and where there is an adapter. So what we say an adapter in an PC or I2C or whatever, you have an SP adapter, I2C adapter, or you have an PC adapter, which is a host bridge that acts like a host adapter, like a controller. You have a host controller or something. So you need to understand all these terminologies and functionalities for your driver to get hooked onto it. So there are so many, we have kept it. But anyway, we have talked about character driver. That's how every driver works. Like you need to register it, like register the device and deregister device. It's very much required, registering the device. And we'll talk about in detail when you go with. There used to be a probe call sequence. So how this device gets initialized. So there would be a probe. So this probe generally will be called by the bus infrastructure, like your serial bus or a PCI bus or whatever. The bus goes and probes each and every device on the bus, and then gets in. Okay, I think I have a device 0 in my serial bus or PCI bus. Okay, I know who is he is having an register. I'll go and register mechanism. So he calls the registers. He has operations get registered. So this all will be handled in the boot time in BIOS, mostly by the probe call. So you have a probe within your driver saying that when I probe, I want to call device init or whatever. So that's how you go and add your registering mechanism. So the device or the driver gets populated for the device. So we'll talk about when we go through it. The probe is very important framework when you do a device driver. So you need to understand how a bus works, or a bus adapter. Anyway, it will be like host bus adapter, which goes and probes your devices and populates it. Yeah, so we are talking about this probe. So we are saying what a probe does. It just initializes the device, maps the IO memory, registers the interrupt handler for the device. So this all will be provided by the bus infrastructure. So when you say bus infrastructure, when you talk about in network, you will see this all will be done by the PCI, right? You can understand when you see this picture, okay, what this all talks about. See, when you say the ALSA driver or anything, whether it's a sound driver or whatever, internally it uses a PCI device. So the PCI device goes and probes it and climbs the device. The driver generally climbs the device and adds to your network. So you have a PCI adapter driver. That's a bus infrastructure driver that calls a general PC core bus, and that bus goes and calls your device driver, and device driver goes and climbs the device for you. Okay, this driver is for this device. I'm climbing it, and it adds onto your general device tree. So when you see a device manager, everything you see, all the devices gets populated. This is a typical way it happens. Your sound card is attached. You have a PC adapter card which goes to the PC core, goes and probes there is a driver for it, ALSA driver, and ALSA gets added onto it. That's how any device will generally happen. Okay. With that being said, we'll just jump over to Wi-Fi drivers and just give an overview of it. Okay. So this, if you understand this mechanism, everything is clear. How typically internally and hardware works. You need to know the understanding. Like only then you'll know. I don't know what is a PCI core, how this device is driven. Okay, you would be writing only your driver here, but this driver, how it is invoked, it internally still bothers with these two guys which you are not even aware. But you might need to have some interface functions and mechanism to do handshaking with these guys. So you need to understand the whole framework for you need to see how your driver fits into your framework, right? Okay.